Hello everyone. I'm Gitanjali Jaina. I'm at PhD School at IIT Delhi. I welcome you to the second live section of this course, Introduction to Laser. I have unmuted all. Can anyone please confirm whether my voice is audible or not? Is my voice audible to everyone?
Yes, ma'am.
Okay, thank you. So in each section, what we will do, we'll go through the concept, or we'll first go through the concept that has been taught in this week, and I will clarify the doubts, whatever you are having in this course, as well as I will clarify the doubts which you all might have for the assignment that has been uh, posted in the discussion forum or in the NPTEL site. So in addition to that, if we have time, then we will discuss some additional problem that will help you to understand the concept. So let us wait for 5 more minutes so that everyone can join, then we'll start the section. So before that, is there any doubt for the previous section? If you have doubt, then let's discuss now. Otherwise, we will start the section directly. Let us share my screen first. So in the previous section, we saw the different type of light matter interaction, like spontaneous emission, stimulated emission, stimulated absorption, and how the rates of this spontaneous emission as well as stimulated absorption as well as emission, how they are depends on the atomic population, as well as we studied about the Boltzmann concept. Let me go through the uh, previous section slide ones. So the previous section, we, so we saw what is laser, what are the different properties of a laser, as well as uh, we saw what is monochromaticity, different kind of sources of light, as well as how the line width varies from one light source to other light source. Mm, then we uh, studied about the absorption spectrum as well as the emission spectrum. Then we see what are the different spectral series of a hydrogen atom, like Lyman series, Balmer series, Bastian series, Brackett, Pfund series, and how the rate of absorption during this transition, like when atom takes excitation from lower level to high level or from high level to low level, how the rate can be expressed in terms of the atomic population as well as spectral energy density. So, and we are based on the equilibrium condition, we derive the two Einstein relation as well as the two Einstein coefficient. So these are all what we see in the last section. So in this section, we'll see the atomic Lensing function, and as well as we will see the how this why this atomic Lorentz function is there during the spectrum, and what are the reasons that we are getting a broader spectrum in comparison to a narrow spectrum. So it's already 4:05. So let us start the section. So let's revise some of the important concept of previous section. So in previous section, we have considered, let's say we have two-level atomic system. If you see the left figure, right figure, if you see it, then this is the representation of a schematic of a two-level atomic system, which is energy E1 and the first excited state energy E2. And the atomic population in E1 is N1, and the atomic population in the higher excited state is N2. Now, when a radiation interacts with it, then we can have two processes. One is absorption, and another one is emission. So, emission can be two types. One is spontaneous emission, and another one is stimulated emission. And we saw how the what is the rate of this spontaneous emission and stimulated emission and absorption. So let's see for the stimulated emission case and stimulated absorption case, we have, let's say for stimulated emission, we have the rate equation is B21 U nu N2. So B21 is the rate constant for transition from 2 to 1, and U nu is the spectral energy density that we got from Boltzmann distribution, and N2 is the atomic population of the first excited state. And for the stimulated absorption case, we have B12 U nu N1. So N1 is the atomic population of the first excited state, and U nu is the spectral energy density, and B12 is the rate constant of a transition from 1 to 2. So before going further, so let me tell you, whenever you have any doubt, whenever I'm explaining something and you have some doubts, then please free to stop me at that time and ask your doubt. So I think I have unmuted it all, or if not, you can also write in the chat box so that I can unmute you and you can ask your question. So please free to stop me anytime so that you can clarify your doubt. And let's see what is the rate of the spontaneous emission case. So for spontaneous emission, it doesn't depend on the radiation. So that's why we have two constant. One is A, which is the rate constant for 1 to 2 transition, and N2 is the population of the higher excited state. So now by equating at thermal equilibrium, what will happen? The rate of upward transition will be equal to the rate of downward transition. So upward transition will take into account the absorption process, and downward is emission process. So if you put the rate equation for absorption as well as the emission, the spontaneous emission as well as the stimulated emission, but what you will get? You will get a Einstein relation. So we got this relation by taking a non-degenerate two-level system. Okay, so by taking this all these condition, we found that the rate constant, that is B12 and B21, are equal, and we can remove the indices 1, 2, and 2, 1 and write it as B only. Similarly, we represent the rate constant for the stimulated absorption case as A instead of A21. So from that, we got the equilibrium. We got the what are the Einstein relation, which is A by B equal to 8 by h nu q by cq, and A equal to 1 by TSP. So, so from that you can see A is related to the spontaneous emission lifetime of the spontaneous emission process. And if you know, and TSP is measurable, as we see in the last class, we can measure the TSP experimentally. From that, we can get the value of A. And after we got the value of A, by using this relation, A by B equal to F by H nu Q C Q, we can get what is the value of B. So in this way, we can get what are the rate constant for a absorption and emission case. So before going into the concept of this week, let us go through three questions. So that will help you to understand the concept as well as the revise the concept. So let me go through the first question. Question one. So question one is which one of the following is not a property of a laser beam? So it is asking about which property which are listed below is not a properties of a laser beam. The first option is highly coherent. So we have seen ki, the laser light is highly coherent, which are characterized by coherence time and coherence length. So it is not the answer. So if you see the second option, it is telling the laser beam is highly divergent, which is not the case. So laser beam has narrower divergence angle. So this means that these are not highly divergent. So it means the answer is this highly divergent. Let us see the other option also so that we can confirm yes, it is the answer. So the C is highly monochromatic. So you know laser is highly monochromatic, and the D option is it has high intensity. So you all know it is high intensity because the energy is more confined in a small cross section of the beam. So it means it is high intensity of light. So this means the answer is B, highly divergence. And it's one of the easiest question. So let me go through the second question. Second question is, what is the primary mechanism responsible for achieving amplification in a laser? So to get amplification, what is the primary mechanism? What is the condition you need to have to achieve amplification? So the first option is spontaneous emission. Second is stimulated emission. C is thermal excitation and D is optical pump. So as we have discussed in the last class, the primary mechanism for achieving amplification is stimulated emission. So that means the answer is B, stimulated emission. So these are conceptual. Let us solve one of the numerical problem. So I will give you some time to go through the question so that you will be familiarized with the question. Let me read out the question for you. So question 3 is, under excitation by a impulse at time t equal to 0 of switchable energy, the instantaneous population of a particular energy level of an atomic system varies with time. So the graph, there is a graph. So it is showing how the atomic population is varying with respect to time. Okay, so this is the graph that you have. So this is the graph showing how the atomic population is varying with respect to time. So the y-axis, if you see, it is the all the assignment will be MCQ, but the main exam, I don't think it is MCQ. It will have subjective type also, where you can solve the problems and you will show what are the states also. I'm not sure, but let me confirm first with the NPTEL team. Then I will let you know in the next section. But I don't think it will be MCQ type. All will be MCQ type. There will be subjective type first. Okay. So this is, if you see the y-axis, there is a plot between the ln of the population, ln. So y-axis is ln in t by n0 and x-axis is the time. So now it is asking what is the lifetime of the spontaneous transition rate. So it is asking about TSP. So you have this plot. Now it is asking about what will be TSP for this kind of atomic system. So, does anyone know how to solve this problem? If you know, then let me know the steps. Not then I will explain how you can solve this kind of problem. Go through the question once. Okay, so let me solve this problem for you. So it is asking about TSP. So spontaneous emission, you know, the population, atomic population varies with respect to time is this equation. So you can write the population, the variation of population with respect to time is nt equal to n0 e to power minus at. So nt is the population, atomic population at time t. N0 is the initial population at time t equal to 0. A is the, you know, it is the rate constant of spontaneous emission. So for TSP, you know, the lifetime, spontaneous emission lifetime is defined as the time at which the NT becomes N0 by E. So this means when you have this condition, you know that the time at that moment is the spontaneous emission lifetime. So now you can write, you can take ln in both sides. So if you take ln nt will become ln n0 by E. So use these properties of logarithm so that you can get ln n0 by equal to ln n0 minus ln e. So ln e, you know, it is 1. This one is 1. And if you take ln n0 to this side, then you will get ln n2 nt minus ln0 equal to minus 1. So the final equation you will get is ln nt by n0 equal to minus 1. So this means that when this condition is satisfied, the time at that moment is the spontaneous emission lifetime. So for spontaneous emission lifetime, you have two condition, you have two equation. One is the time at which the nt becomes n0 by e, or you can write it in terms of the ln as ln nt by n0 equal to minus 1. Now, if you see the graph that is given to you can see the ln nt by n0 is minus 1 here, right? So that means the time at which it is minus 1, it is the spontaneous emission lifetime. So it is, if you see, for minus 1 in the y-axis, it is 8 in the x-axis. So this means the time is, and the time is in terms of 10 to the minus 8 order. So if you see, it is 10 to the minus 8 order, 10 to the minus 8 second. So that means the spontaneous emission lifetime is 8 into 10 to the minus 8. Okay. So now in this way, you can calculate how to calculate the spontaneous emission lifetime of a process when you have a graph. When you are given a graph, then you can easily find out what is the spontaneous emission lifetime. From this, if a further question like what is A in the system, so you can calculate A is 1 by TSP, and from that you can calculate what is the B value by using the Einstein relation, which is A by B equal to 8 by h nu cube by c. So you can see by calculating only one factor, one parameter, you can calculate the other parameter in the system. So is this question clear to you? If it is clear to everyone, then I will move to the concept that has been taught in the class in this week. Okay, so let us go to the concept that is taught in this week. So in this week, so let's see what is the emission in absorption spectra of a process, absorption process or emission process. So let us take one two-level energy system where the lower level is E1 and the higher level is E2. And the population is N2 here and the population is N1 here. Now, if you see the emission process, that is when an atom make a transition from higher to lower state. Let's say it is radiating its energy in terms of photon. So that means one photon will be emitted, which will be H0, and H0 will be equal to E2 minus U1. So this is the emission process. Now, if you want to look at the emission spectra, what kind of spectra will get if you see the emission spectra, then what you expect? You expect that in this emission spectra, which is a, if you see the rightmost figure, which I am highlighting, this one. So let me this figure. You expect that the line spectra will have only one line, which is around the frequency nu zero. Okay, so nu zero is nothing but the energy difference between the levels E2 minus E1 by H. So you expect that there will be one line in the emission spectrum. But in reality, what we see that the emission spectra somewhat look like this. So let me erase this one. So if you see in actual spectrum, the emission spectra look like this. Like there is a broadening of the spectrum around this allowed transition. So we have nu zero, which shows the transition from E2 to E1, which we call atomic resonance. So we see in the emission spectrum, there is a spreading of the spectra around this nu zero. Okay. So if you take one example, let's say we have sodium lamp. So sodium lamp we use in the Newton's ring experiment. So for this sodium lamp, we have two spectral line. One is D1 line, other one is D2 line. So D1 line is the line at which the lambda is 5890 angstrom, and D2 line is the spectra at wavelength 5896 angstrom. Now, if you look this spectra under high resolution, what you will see? You will see that these lines have certain finite width around this wavelength 5890 and 5896. So you see there is a spreading of the emission spectra around this wavelength. So this indicate that whatever atoms that is interacting with the radiation, it is not interacting at a particular frequency nu zero. It is interacting with the radiation over a range of frequency. So in addition to nu zero, it is interacting with the frequency nu zero minus delta nu and nu zero plus delta. We'll see in later that what are the reason behind this spreading and how we can quantify this spreading. So similar to the emission spectra, now we'll have absorption spectra. So similar to emission, we will have in the absorption spectra, we will have dips in the spectra, and instead of a line, we have a broadened line, which are around the allowed transition. So let's say here there are two lines, means let's say we have three energy level, which is E3, E2, E1, and the transition from this to this is lambda 1, and transition from E3 to E1 is lambda 2. So we'll see that in the absorption spectra, around this line, lambda 1, lambda 2, there will be spreading of the spectra. So this means that the atom interacts with the radiation over a range of frequency. So now to explain this spreading of this line spectra, we define a function which is atomic line set function g of nu d nu. So g of nu d nu, it basically it tells us about the probability that an atom interact with a radiation between frequency nu to nu plus d nu. So we see that entire spectra has a broadening. So this means that the atom is interacting with the radiation with frequency nu, and there is a finite width around this nu plus d nu. So that's why we define a function g of nu, which tells us about the probability that one atom will interact with the radiation in the frequency range nu to nu plus d nu. So this is the function that we define to explain the broadening in the spectrum and the mechanism that leads to such kind of broadening. We call it as a line broadening mechanism. So later we will see what are the different types of line broadening mechanism and what are the different conditions under which we will see this line broadening. So let us see the atomic lines and function once again, which is g of nu du nu. So as you have seen, g of nu du nu is the tells us about the probability that one atom interact with the radiation from frequency nu to nu plus 10. If you see the graph here, this is the probability distribution that one atom will interact with the radiation. Okay, so with in this graph you see a peak here. So peak here it indicates the probability of the atomic resonance. Let's say if you see this figure, this is two-level atomic system, which is energy E1 and E2, and there is a atomic resonance associated with this level. Let's say which atomic resonance, it's basically a frequency that is equal to E2 minus E1 by H. So the peak here corresponds to this frequency where the probability is maximum. And in addition to this atomic resonance frequency, there is if you see a small region between nu minus delta nu to nu plus delta nu, see the probability is non-zero. Here the probability non-zero. And for higher frequency, that is far away from this atomic resonance, the probability is almost zero. If you see the higher result, the probability is almost zero. Now, as g of nu is the probability, so you know that the total probability will be always equal to 1. So if you express it in terms of the normalization condition, what we'll have is this normalized condition for the line set function. So it means if we have an entire spectrum where all kind of frequencies present, like nu1, nu2, nu3, all kind of frequency, and if you integrate this probability over all this frequency, then what we'll get? We'll get 1, because total probability is always equal to 1. So the atom will always interact with the radiation in the entire spectrum. So this is the normalization condition for the line set function. Now we'll see how by including this line set function, how the rate that we have seen earlier, how they will be affected by in the presence of this line set function. So first we'll see the spontaneous emission process. So for the spontaneous emission, let's say we have two level, same two-level energy system, atomic system, E1 and E2. And we have seen that the rate constant for this level is AN2 in the absence of the line set function. Now, if you see, let's say we want to find out what is the total number of atoms that will interact with all frequency. So, to see this, let's take N2 G nu d nu. So N2 G nu d nu is nothing but so G nu d nu is the probability that one atom will interact with radiation from nu to nu plus d nu. So if you multiply it with N2, so this will give what is the total number of atoms that will interact with the radiation from frequency nu to nu plus d nu. So this is what written here. Here, So N2 G nu D nu is the total number of atoms that will interact with the radiation in a small frequency interval, nu to nu plus D nu. Now, if you want to find out what is the rate in this small interval, that is nu to nu plus D nu, what you have to do? You have to just multiply it with the rate constant A. So if you multiply it with rate constant A, so we'll get what is the rate of the spontaneous emission in this small interval, nu to nu plus D nu. So after that, if you want to find out what is the total number of spontaneous emission per unit time per unit volume, which is nothing but the rate of the spontaneous emission. So that you can get by integrating this rate constant for a small interval. So if you integrate it, what you will get A into G nu D nu integration. So A into is constant, you can take it out from the integration. And by integrating G nu D nu, we'll get a value of 1. This means that the rate constant, the rate of the spontaneous emission is A into, which is what we have seen earlier also. So in earlier, when we didn't consider the Lensing function, the rate constant is always A into. So now by including G nu D nu, we see that the spontaneous emission rate equation is A into. So let's see how the stimulated process will get affected in the presence of this Lensing function. So stimulated process is to include two processes. One is stimulated emission and stimulated absorption. Let's see the stimulated emission first. So similar to so first we'll consider small interval nu to nu plus D nu, then we will integrate it so that we can get the total rate. So let's see the rate equation for a small interval nu to nu plus D nu, which you can represent it as d of gamma, not gamma, it is, let's say y to 1 equal to 1 u your 2 u nu and 2 g nu d nu. So this is the rate of stimulated emission between frequency nu to nu plus d nu. So previously what we had the rate of stimulated emission is B21 nu nu N2, and there is no G nu D nu term in that equation. But now if you consider the Lansing function, the rate will be this. So to find out the total rate, that is total number of stimulated emission per unit time per unit volume, what you have to do, you have to integrate over the whole volume. So if you integrate it, what you will get, B integration of B21 u nu and 2 G nu D nu. Now you see in the equation there are two functions. One is spectral energy density and another one is Lansing function. So this all depends on the frequency. So next we'll see how we can simplify this equation. And similar to the stimulated emission case, in the absorption case, if you want to find out what is the number of atoms that is interacting in the frequency nu to nu plus D nu, what you have to do, you have to multiply N1, that is the atomic population of this lower level with the probability. So N1 G nu D nu will give the number of atoms that interacts with the radiation between frequency nu to nu plus D nu. And if you want to find out the rate for that interval nu to nu plus D nu, we have to multiply it with the spectral energy density because absorption occurs in the presence of radiation. So that's why we have spectral energy density here. And there is a rate constant which is B12. And to calculate what is the total number of absorption per unit time per unit volume, what you have to do, we have to integrate it over the total volume and we'll get an equation like this. That is integration of B12 u nu N1 G nu D nu. So this is the expression for total number of absorption in the presence of Lansing function. Now we'll see how we can simplify this two equation, which is gamma 21 and gamma 12. So if you see, so gamma 1 to gamma 21 is nothing but b and 2. B and 2 is a constant, so we have taken it outside the integration. And there is two function that depends on the frequency. That is, one is spectral energy density, and another one is line step function. And similarly, for the absorption case, we have gamma 1 2, which is bn1 integration of 0 to infinity u nu g of nu d. Now, in this expression, the u nu, which defines the spectral energy density of the incoming radiation. So, incoming radiation can be a broadband source, or it can be narrowband source. So, this means that we have two cases. The first case, we have u of nu as a broadband radiation, like the thermal radiation from, let's say, we are taking tungsten halogen lamp. So for that, it is a broadband radiation. And if we take narrowband radiation, like laser radiation, we have nu as narrowband. So we have two cases. One is the case where nu is broadband. If you see the figure 1, it's the spectrum of it's the emission spectrum of tungsten halogen lamp. If you see, there is a emission radiation from 0.2 micrometer to 2 micrometer, and this is broadband. And in the second case, we have a laser radiation where the spectrum is much narrower than the tungsten halogen lamp. So we'll consider these two cases and find out how to simplify the rate equation. So let us consider the first case, which is the case where we have broadband radiation. So for this case, if you see the right figure, if you see this figure, so this shows the spectra of a broadband radiation as well as how the lines of function is varying with respect to frequency. So let's say we have two energy levels, uh, which is E2 and it is E1, and the atomic resonance frequency is nu0, and nu0 is nothing but E2 minus E1 by H. So this is the atomic resonance frequency. So for this, if you see the graph, you see that the G nu is 0. If you see it in this region G of nu is 0. So that means there is no contribution of u nu in this region. And only the region, like if you see this small region where the G nu is touching the u nu. If I maximize, let me highlight it. So if you see this region, there will be the spectrum of u nu will be like here, and there is G of nu which varies is this. So if you see this small region, in this small region, you can consider the u nu, the variation of u nu as constant, and you can take it as the spectral energy density around the resonance frequency. Okay, so that is what we have done in this integration. We are taking u nu as constant, which is u of nu 0. And G of nu is depends on the frequency. So if you now integrate it from 0 to infinity, what we'll get? We'll get a value of 1. So this means that we can write the stimulated absorption case as gamma 1 to equal to bn1 u of nu 0. So you now see how the line step function is affecting the rate equation. So previously, if you go through the previous section, you know that if you will see the gamma 1 2 is nothing but b and 1 only. And there is no spectral energy density there. There is no u nu 0 factor there. But now when you consider the line step function, the rate equation get modified and we have b and 1 u of nu 0. From this, if you want to substitute the b constant, you can take the expression from the Einstein relation, that is A by B equal to 8 pi h nu q by c. So from this equation, we'll get B equal to CQ by 8 pi h nu q 1 by TSP. So 1 by TSP, we are, it is, it is A. A is equal to 1 by TSP. So by putting the value of A and the B value, we can now represent the gamma 1, 2, that is the rate for the stimulated absorption as this expression. CQ by 8 pi h nu q 1 by TSP, U of nu 0 and 1. So this is for the broadband case. Now we'll consider the narrowband case, where let's say we have a laser radiation and how the rate equation will get affected in the presence of a laser radiation. So for this case, now what we'll have, if you see the graph here, so now you are seeing the spectral energy density, that is U of nu is narrower than the line shape function. So that is what shown in this figure. If you see the black curve, it is spectral energy density, and the red curve is the line shape function. Now, if you see the G of nu is much, it is much broader than the line shape, the spectral energy function. So for this case, what we can do? Similarly, if you 1 minute, if you zoom this section, so if you see this section, there will be variation of nu like this, and there will be G of nu, which varies like this. So in this small region where the G of nu and the U of nu is intersecting with each other, you see that you can treat the G of nu as a constant. And this constant, we can take it around the resonance frequency nu of L. So nu of L, as I said before, it corresponds to the energy difference between the two energy levels, E1, E2 minus E1 by H. Okay. So if you take now in this case, we can treat, instead of U of nu as a constant, we can treat G of nu as a constant. And so that is what we have done here. So we have taken out G of nu and G of, now we have G of nu L and one integration of U of nu d nu. And this total integration of U of nu d nu, we represent in terms of U of nu, which is nothing but the total energy density. That is the energy density per unit volume. Okay. So total energy density, you can also U of nu, you can write it as n times h nu by b. So h nu is the energy density of one photon, and you have n number of photons, then you can write it as n times h nu by b. So this is one expression for U nu. This is for the case stimulated absorption, this equation. Now for the stimulated emission case, where we have N2 N2 instead of N1. So we can write the rate equation is gamma 21 equal to B into G of nu L U nu, where B is this constant. Okay, so now you see, let us summarize what we got, the rate equation in the presence of the line shape function. So for the stimulated emission case, we got gamma 21 is this expression where we have N2 U nu L G of nu, and there is a constant here. And for the stimulated absorption case, we have a constant multiplied by N1. So this we are treating as a constant multiplied by N1. So this whole term you can write it as omega W1 to N1. So so the final expression will be like gamma 21 equal to omega 21 into and gamma 1 to equal to omega, not omega, it is W1 to N1. So this is the final expression for the rate equation in the presence of a line shape function. So this is all about the rate equation in the presence of a line shape function. So till now, any of you has any doubt? Otherwise, we will move to the amplification process. If you have any doubt, you can write in the chat box, or you can unmute yourself also, because I have unmuted all of you, so you can ask your doubt anytime. Okay, if there is no doubt, then let us move to the next part. So in the next part, we see what is the we'll see what are the different condition that is required for a amplification process. So this is what we derived in the previous slide. So we have gamma 2 1 is a rate equation for stimulated emission case, which you can represent it this. And this is the gamma 1 2 is the rate equation for the stimulated absorption case. And you simplify this equation as omega, sorry, W 2 1 and 2, and we simplify it as a W 1 2 and 1, where W 1 2 and W 1 2 is this expression. So now let us see a medium, a laser medium, where we'll get amplification process. Okay, if you see the schematic, so the box here is a laser medium where the light interact with the radiation. And now we are taking one nearly monochromatic radiation around the frequency nu. And we are now we'll see how the laser medium will get amplified in the presence of this nearly monochromatic radiation. In this case, this I in is the intensity of the radiation at the input end, and I out is the intensity of the radiation at the output case. So for amplification, what we require I out should be greater than I in. Now we'll see under what condition we can achieve this condition for amplification. So to derive the condition for amplification, we'll take one small cross section of the medium. Let's say a small cross. If you see this figure, we have taken one small cross section which is surface area is S, and there is a line segment dz in the propagation direction. So if you find out what is the volume element for this cross section, the volume will be S dz. And now in this case, if you want to find out what is in this small cross section, how the stimulated emission and how the stimulated absorption, how uh, uh, emission and absorption process are going on this small cross section. If you want to find out, then what we can take the help of whatever we have derived before, like gamma 1 2 and gamma 2 1. So if you want to find out what is the number of stimulated emission for this in this small cross section, then we can gamma 2 1. It is nothing but what is the number of stimulated emission per unit volume per unit time. So if you want to find out what is the number of stimulated emission per unit time in this volume STZ, what you have to do, you have to multiply the volume element of this cross section. So if you multiply it, it will be gamma 2 1 SDZ. Similarly, if you want to find out what is the number of stimulated absorption in this small element SDZ, we have to multiply SDZ with the rate equation gamma 1 2. So this is the number of stimulated emission and number of stimulated absorption per unit time. Now, if you want to find out what is the energy that is generated in this small cross section, what you have to do, you have to multiply the number of stimulated emission with the energy of one photon. So these are the number of stimulated emission in the cross section. So if you multiply with h nu, what we'll get? We will get what is the energy that is generated per unit time in this small cross section is dz due to the stimulated emission process. Similarly, if you want to find out what is the energy absorbed in this small cross section, what you have to do, you have to multiply the number of absorption per unit time with the energy Hν. So if you multiply it, you will get what is the energy absorbed in that small cross section. So in this small volume, you have this much amount of energy that is generated and this much amount of energy that is absorbed. So the net amount of energy that will be generated in this small volume will be nothing but the difference of this energy. So energy generated minus energy absorbed. So this is the final expression of what is the amount of energy that will be generated in this small cross section. So this we derive it by using the help of the rate equation, the gamma 1 2 and gamma 2. And another way where you can find out what is the energy generated is by taking the intensity. By taking the intensity of the radiation, you can also find out what is the energy generated in this small cross section. So let's say we have I nu Z, which is the intensity of the incoming radiation in this small cross section, and I nu Z plus dz is the intensity of the radiation that is leaving this cross section is dz. So intensity, you know, it is what is it? It is power per unit area, nothing but energy per unit time per unit area. So power is unit energy per unit time. So intensity is energy per unit time per unit area. So if you want to find out what is the energy per unit time, what you have to do, you have to multiply intensity with area. So area of this cross section is S. So that is what written here. So this means if you have intensity I that is entering the cross section S dz, so the energy entering the volume element will be I nu S. Similarly, I nu Z S. Similarly, if you want to find out what is the energy leaving the volume element, what you have to do, you have to multiply the output intensity with the area. So we have I nu Z plus dz as an intensity that is leaving this area. So let me take a different color. So I nu Z plus dz is the intensity that is leaving the area, and S is the area of this volume element. So this means this is the energy leaving this small cross section as dz. Now, if you want to find out what is the net energy, we have to take the difference of this energy, that is energy leaving minus energy entering. So this is what written here. So this means the net energy leaving this volume element will be I nu Z plus dz minus I nu Z S. Okay. So if you now, so dz is a very small cross section. So when dz is small, you can expand this expression I nu Z plus dz as Iz plus dou I by dou Z into dz. This is only for small cross section. So you can now put this final expression here. To put it here, the Iz here and Iz here will cancel out. And what we'll have? We will have dou I by dou Z into dz equal to dou I by dou Z as Z is the net energy that is entering, that is leaving the volume element S dz per unit time. Okay, so this is what we derive it using the intensity of the radiation. So now we'll have two equations. One is equation 1 where we have calculated the energy generated using the rate equation. And in this case, we have calculated the energy generated using by taking the intensity of the radiation. Now they are equal, so we can equate this two equation 1 and 2. If you equate it, what you will get is this expression, which is dou I by dou z equal to gamma 2 1 minus gamma 1 2 H. So this is the final expression we'll get. Now we just have to put the constant value of gamma 2 1, gamma 1 2 to find out this expression. Okay. In the next step, what we have done, we have replaced u nu as n T by is n I nu by C. So we can write the spectral energy density in terms of the intensity as n I nu by C. So if you put it the I nu here by if you put the u nu by the intensity expression, what you will get? You get that dou I by dou z equal to this expression. So now if you see there is dou I by dou z here and I nu here. And now we know that this intensity is only a function of z. So we can replace this partial derivative by total derivative dou I nu by dou z. And by taking this I nu here to this side, what we'll have? We will have dou I nu by dou z. So dou I nu by dou z equal to gamma nu I nu z. So gamma nu is nothing but the constant. This is the expression for gamma nu, and there is I nu here. So if you now solve this integration, what you will get? You will get I nu z as I nu 0 e to bar gamma z. So this is the final expression for the intensity. How the intensity is varying when it propagates through the length of this laser medium. Okay. So if you have laser medium, let's say it is z equal to 0 and z equal to L, and you have I nu 0 as input intensity here. So now if you want to find out what will be the I nu z here, so I nu z will be nothing but I nu 0 e to power gamma z. This way you can find out what will be the intensity of the radiation at a particular length z. So let's see how so for amplification what we need that the radiation that is emitting, that is leaving this volume, which is I nu z must be greater than radiation that is entering. So you require I nu z must be greater than I nu z. So under what condition this will happen? This will happen when the exponential term it is positive. So that means the gamma nu is greater than 0. So this means that the amplification will occur whenever we have this constant gamma nu is greater than 0. So gamma nu, if you see, let me show you this. So gamma nu is given by this expression. If you see this expression, there is g of nu c by n square 8 by nu square tsp, and as well as there is a n2 minus n1 here. So what I have done, so gamma nu will be positive. There is a difference factor here, n2 minus n1. So gamma nu greater than 0, it implies that n2 must be greater than n1. So this indicate that for amplification in the laser medium, we require that the N2, that is the population of the higher energy state, must be greater than the population of the lower energy state. And this is known as this N2 greater than N1. This condition is known as population inversion. So why we call it as a population inversion? Because if you see the equilibrium condition, if you say you are at room temperature, then what we see in that case, if you go through the previous section also, we have derived that the N1 is always greater than N2. This is the equilibrium case. Now, for the amplification process, what we want to achieve? We want to achieve a condition where the population of the higher energy level is greater than the population of lower energy level. So that is why the population is now getting inverted. That is, the population of higher energy level is greater than the population of lower energy level. That is why we call it as a population inversion. So for amplification, we require this condition of population inversion. And in the other extreme, if we don't have gamma is greater than zero, if we have gamma is less than zero, so that means the intensity that is leaving the volume, it is less than the intensity that is uh, entering the volume. So intensity that is leaving is less than the intensity that is entering. That means there is a loss in the system. So that is why we define it as a loss condition. So this is what we need for the amplification process. Later we will see another condition where we require that not this condition is sufficient for the amplification process. Okay. So this is the 1 minute. So this is the condition for the amplification. So now let us see one example. Okay. After this, we'll go few questions, 3 questions, which are related to this concept. So let us see what is small signal gain coefficient. Okay. So we are now examining a system where the light is passing through the laser medium only once. So it is passing through the active medium where the amplification is going on only once. So for this case, if you want to find out what is the gain, so gain is nothing but output by input. So output expression, you know that I nu Z equal to I nu 0 e to power gamma Z. So if you want to Z or L, anything. So if you want to find out what is the gain, gain is nothing but output by input. That is I nu L by I nu 0. So gain is expressed as e to power gamma L. So this is the expression for the gain in the system. And where gamma is the gain coefficient. And if you see the dimension of the gamma has dimension of meter inverse. Okay. So, and this is the expression for the gamma, which we have seen earlier. Now, if you write this expression, you can simplify it as you can write n2 minus n1 as delta n and other factor is sigma nu. So sigma nu, so now what we have done in the next step, we have simplified this expression as sigma nu delta n. So sigma nu, if you see, this is nothing but the cross section for the stimulated transition. So this is unit of area. So let's see why this sigma nu has a unit of area. So n, you know, n is the number of atoms per unit volume. So it is dimension of volume, and the gamma nu has dimension of meter inverse. So this n has volume minus q, and this gamma nu has volume minus 1. There is a constant here. You want to find out what is the dimension of this constant. So this means that if you take m to this side, so this is dimension of m square. Okay, so the constant c, which we write it as sigma nu, as a dimension of meter square. So this it represents the cross section for a transition process. So that is why we define sigma nu as a cross section for the stimulated emission or stimulated absorption. And if you see this expression, so let me erase so that it is clear to all of you. So, so the delta n here, it is not a constant. We'll see later. The delta n, that is n2 minus n1, it's not a constant. It depends on the intensity of the incoming radiation. So we'll see in the subsequent section that delta n, you can write it as delta n equal to delta n0 1 plus I nu by Is. Okay, so delta n, it depends on the intensity. Now if we consider a case where the I nu is much less than Is. So I nu is nothing but the intensity of the incoming radiation, and Is is the saturation intensity. We'll see what is saturation intensity. So for now, let us take a case, the case where I nu, the incoming radiation is much less than the saturation intensity. So if you see the expression delta n equal to delta n0 1 plus I nu by Is. So if you see the expression, so In is much less than Is. That means you can neglect this term. So what will have you have delta n is delta n0. So for this case, the gain coefficient, which is gamma nu, you can write it as sigma nu delta n, and delta n is nothing but sigma nu. Delta n is delta n0, and this gain coefficient, we represent it as gamma 0 nu, which is nothing but the small signal gain coefficient. So this is the gain coefficient where the incoming radiation is much less than the saturation intensity. So, and uh, let us see what are this saturation intensity and what is this saturation gain coefficient. So if you take the expression gamma nu equal to sigma nu delta, which we have here. If you see this expression, gamma nu is sigma and delta. So now you put what is the expression for delta n? Delta n is delta n0 1 plus I nu by Is. If you put it, you can get the numerator as sigma n delta n0. This sigma delta n0 is nothing but the small signal gain coefficient. So that is why you can write it is gamma 0 nu divided by 1 plus I nu by Is. So what is the final expression we have? We have the gain coefficient as gamma 0 nu 1 plus I nu by Is. Now if you see this expression, if you want to plot it, then we will get a plot like this. So for small intensity of the incoming radiation, that is for the case where I nu is much less than Is, you see that the gain coefficient is almost constant in this region. If you see this region, it is almost constant. Now, when the incoming radiation intensity gradually increases, we'll see that the gain coefficient now will decrease. Okay, so it will decrease like this. In this graph, if you see the case where I nu is equal to Is, that is the intensity of the incoming radiation is equal to the saturation intensity. So for that case, we have gamma nu as gamma 0 nu divided by 2. So this means that the saturation intensity is the intensity of the incoming radiation, for which we will get a gain which is half of the uh, gain, a small signal gain coefficient. Okay, so gain will be half in this saturation intensity. So this is the definition for saturation intensity. Now to summarize, let us see what we have seen so far. So gamma nu is gain coefficient, where you can write it as this expression, and we have now In this expression, if you take what are the variables of nu, so the variables of nu is g of nu, which is the line set function, and nu square is the frequency of the square of the frequency of the incoming radiation. So we can write it as gamma nu will vary as g of nu divided by nu square. But g of nu, if you look at g, what is the variation of g of nu? It will be like a probability distribution function, which is zero when we go far away from the atomic resonance frequency, and only around this atomic resonance frequency, the probability is non-zero. So if you plot this g of nu and nu square in one graph, what you will get? If you see this graph, so g of nu is varying like this, and this is the variation of 1 by nu square. So this means that the this nu square variation in this, when g of nu varies like this, the nu square varies like this. If you see this region where g of nu is non-zero, you see that you can take this nu square as a constant in this region, small region where g of nu is non-zero. So that is why we can neglect this 1 by nu square factor. So that we have done, this is what we have done in this next step. So what we got? We got that the gamma nu variation, that is the gain coefficient, you can write it as it is directly proportional to the line set function g of nu. Okay. And the other important concept is in the previous case, we discussed that the for amplification process, we require that the population inversion should be there. That is the N2, the atomic population of N2 should be greater than N1. But in that case, what we have considered, we have considered that the B12 is B2. So we consider that the rate constant of stimulated absorption is equal to the rate constant of stimulated emission. 1 minute. I think my screen is not visible to you. So let me share my screen again. Please wait for 1 minute. What's the problem? Mhm. So till now, in the meantime, I can ask, do we have any doubts till now? Any doubts till now? You can ask or you can write in the chat box also. Okay. There is one question. Can you tell the relation between the gain coefficient and the intensity of the radiation? Um, So we have seen the gain coefficient is independent of the intensity. So only the delta n, which is n2 minus n1. So that factor only depends on the intensity. Okay. So let me show you first and we'll discuss. The gain coefficient, it is independent of the intensity. If you see the expression for the gain coefficient gamma nu, you will see that the gain coefficient is independent of intensity. Any other question? I think your doubt is clarified, right? Rohan, Vishal, your doubt is clarified, right? Or you have any other? Does anyone have any other doubt? So I'm trying to log in my iPad, but there is a problem. Okay, now let me save my screen. So I think now my screen will be visible. Yeah. So Vishal, do you have any doubt or you are not? The question we have asked is it is the did you get the answer? So in the okay. So let us see. So previously we have seen for the amplification process we require N2 must be equal to N1. But this is not the condition. I mean, this is not the case for all times. Like for that, what we assume we assume that B12 is equal to B21. So if we have B12 equal to B21, so in that case we have N2 that is greater than N1. Okay. Now, if you consider a system where we have doping in the system, like solid state laser. If you consider, let's say, erbium silica, where erbium are doped in the silica matrix, what we have in that case is there is, instead of this discretized energy level, we have multiple energy level because of this doping. So because of that, in this multiple energy level, what we have? We have B12 not equal to B2. So for this kind of system, we have this rate constant which are not equal. So for this case, the cross section of the stimulated absorption as well as the cross section of stimulated emission, these are not equal. So if you see the graph, this is the graph of the cross section for let's say for the rate curve is the for the stimulated absorption case, and in the black is the stimulated emission. So if you see the graph, there is no these are not equal. So the emission spectrum, the emission cross section is slightly red shifted as compared to the absorption spectrum, as compared to the cross section for the absorption process. So for this case where the sigma is not equal to sigma f, if you if you take this expression, so let me tell you where you can find this relation. So this is the relation here, gamma nu. In this case, what we have considered is, let me go to the this one. So we have gamma is, it is gamma here. So in this equation, we have considered gamma 21 minus gamma 12. So for this case, here gamma 12 is nothing but W21 N2, and this is W12 N1. And we have considered in the next step, we have considered W12 equal to W2. So instead of considering W12 is W21, what we will consider W12 is not equal to W2. So if you take this condition, what you will get? You will get this expression. That is, the gain coefficient gamma nu is equal to sigma E N2 minus sigma A N1. So now for this case, if you want to achieve the amplification process, what you need? You need gamma nu must be greater than 0. So that means the sigma E multiplied by N2 must be equal to sigma A N1. So this condition should be satisfied for the amplification process. So instead of N2 must be equal to N1, now we'll have a modified condition which is sigma E N2 is greater than sigma E N1. So this is the condition. This is the general condition for the amplification process. So this the next graph is the same the graph where we have shown what is the uh, cross section of a absorption process as well as emission process in in a erbium doped silica matrix. So if you see the blue graph, the graph here is the absorption spectrum, absorption cross section, and this is the emission cross section. So now you're seeing the emission spectra and absorption spectra, they are not equal. And as well as there is a slight red shifting of this emission cross section with respect to the absorption cross section. And what the last concept in this is the saturated gain coefficient, where we have considered delta n, which depends on the intensity, is delta n0 divided by 1 plus I nu by Is. And we can write the gain coefficient as gamma 0 nu is 1 plus I nu by Is. So this is what we have seen here. If you see this one, we are discussing this one. Now, if we plot the gain coefficient in terms of the intensity of the incoming radiation, what we'll have for the small intensity, that is when I nu is much less than Is, the coefficient, gain coefficient is almost constant here in this region. But when the intensity now we are increasing the intensity of the medium. So this means that according to this equation, the gamma, the gain coefficient will now decrease in this manner. So if corresponding to this graph, you want to plot what is the intensity variation, this is the variation of intensity as a function of length. The length at which the light is the radiation is propagated. So for small intensity, what you have, the gain coefficient is constant. So that means we have this intensity is a constant. Now this will gradually increase and increase. But after some time, what will happen? The as the gain coefficient is decreasing. So this factor will now decrease. Let's say we are having gamma is 0 now. So that means this will be constant, which is 1. So for that case, we will get a flat line, nearly flat line for the higher intensity. So let us go through some of the problems. The first problem is a lower beam of monochromatic light passes through a laser medium of length 15 centimeter. 15 centimeter. It is given length is 15 centimeter and a monochromatic light is passing through a laser medium. Now it is telling if the optical power of the beam at the output is 9 times the input power. Then what is the small signal gain coefficient of the laser medium? So it is asking about what is gamma 0 nu. Okay. And it is given also the I out. It is 9 times I in. So that means if you want to take the ratio, our I out by I in. So this is nothing but 9. And this expression, you know, it is nothing but e to power gamma L. So if you see this expression, what is it? Uh-huh. Mm, this expression. You see I out by I in e to power gamma L. So we can take the help of this expression and find out what is gamma 0. So there, that means this is 9 equal to e to power 15 is the length, that is length of this medium into gamma. So now if you simplify it, this is not that difficult to find out the answer. So you can get gamma is 2 ln 3 by 15, which is 14.65 meter. And the next question is, an amplifying laser medium has a small signal gain coefficient gamma 0 at frequency mu 0. When the light intensity at mu 0 in the medium increases to a particular level I1, the gain coefficient of the medium reduces to gamma 0 by 6. So we have seen this graph, right? This graph where the gain coefficient is constant, then it decreases with respect to the intensity. So if you see now it is given gamma 0 is the small gain coefficient, small signal gain coefficient at frequency mu 0. And now we are increasing the intensity of the medium, and at a particular intensity, what we got the gain coefficient gamma as gamma 0 by 6. Let's say we are coming here and we are getting gamma as gamma 0 by 6. So it is asking what is the saturation intensity of the medium, that is IS. What is the value of IS? So this, as you know, it is also easier to find out the answer. So what you can do, you can take expression, which is gamma nu is gamma 0, 1 plus I nu by IS, right? And you put the value of gamma nu as gamma 0 by 6. Gamma 0 is gamma 0 only. And I nu here will be I1, right? It is given I1 to a particular value I1. So if you put it and solve this expression, you will get I1 by IS is 5. So that means IS equal to I1 by 5. So this is the expression for saturation intensity, which is I1 by 5. This is the answer. So this is simple. You just have to put the values in the equation. That way you can find out what is the saturation intensity. The last problem, this is this in this we have two amplifying medium. So let me read out the question. The question is, two amplifying medium P and Q are such that the gain coefficient, the small gain, let's picturize this medium. So we have two mediums. What is one is P and another one is Q. So for P we have small signal gain coefficient Y0P, and for Q it is small signal gain coefficient Y0P. And these are related by this equation which are given. So Y0P is 2 times Y0Q, and Y0 is the small signal gain coefficient, and IS is the saturation intensity. The superscript P and Q correspond to the two medium. Now what is given? It is given that at a particular intensity, I nu equal to 3 times of ISP, both amplifying medium have same value of gain coefficient. So this means that this intensity, in this intensity, this both medium, the gain coefficient are equal. And what is asking in this question? The question is the saturation intensity of P, which is ISP, in terms of saturation intensity of Q. What is the value of this? What is the expression for saturation intensity of P in terms of saturation intensity of Q? So let us see what are given to us. So it is given two medium P and Q, and this is the small signal gain coefficient Y0P and Y0Q. And these are related. Now, when we increase the intensity to a condition where I nu is 3 times of ISP, we see that they both have same gain, that is Yp equal to Yq. And you want to find out what is the relation between the saturation intensity of one medium with respect to other. So for that, what we can do, you just have to put what is the expression for Yp, which is Y0P divided by 1 plus this expression, I nu divided by ISP, and Yq is Y0Q divided by 1 plus I nu by ISP. So if you now, in the next step, what I have done, we have to just use this expression here. So 2 times of Y0Q, and this is Y0Q. Now just simplify it by solving this to both sides of this equation. If you solve it, you will get a final expression is 1 plus 2 times of I nu by ISP equal to I nu by ISP. So now you take this one to this side, and I nu is already given. I nu is equal to 3 times of ISP. So in this expression, I have just put what is the ratio of I nu by ISP, okay, which is nothing but 3. So I have put 3 for this expression, and this is remaining as it. So from by solving it, you will get I nu equal to ISP. So you got two conditions. One is I nu is ISQ, and I nu equal to 3 times of ISP. It is already given. So if you want to take the ratio, it is nothing but equal to 3. So in this way, you can utilize, you can use the formulas as well as the condition that is given to you to solve the problem. Okay. So any doubt on this 3 question? Otherwise, we'll move to the next part, which is we'll see what is the different mechanism for line broadening in the system. So I think no one is in doubt. So let us see what is the next concept. So now we'll discuss in deep what are the different mechanism of line broadening. So let's say we have 3-level atomic system, which is discretized energy level E1, E2, and E3. And the atomic resonance frequency of nu1 and nu2. And because of this interaction of the atom, what we get instead of straight line, straight two lines, which is given in this figure. If you see this figure, what we'll get? We'll get a broadened line around this resonance frequency nu1 and nu2. And this type of broadening, like we can divide it into two types. One is homogeneous broadening, and another one is inhomogeneous broadening. So let us see this each broadening in detail. So the first one is homogeneous broadening. The term homogeneous, it means it is identical. So this means in this broadening, this kind of broadening happens whenever the response of each atom or a group of atom is identical. So if you have identical response, then you will get homogeneous broadening in the system. So let's see, let's say we have 2-level atomic system. E1 and E2, and you have the atomic resonance frequency at nu zero. So nu zero is nothing but E2 minus E1 by H. Now in this system we have group of atoms in this system which is picturized in this figure. Now if these atoms, if they have same response, like they if they interact with the radiation in the same manner, then what we'll get? We'll get a single peak around this resonance frequency nu zero. We'll get a single peak, single spectrum here. And now if the number of atoms, so there are three curves that is shown here. The three curves, it correspond to the situation where more number of atom is interacting with the radiation. If no more number of atom interact, the intensity spectrum will increase. So this is the case for homogeneous broadening, where we will get a single spectrum around this resonance frequency. Now, for the inhomogeneous broadening, what we have, the in this case, the atoms or the group of atoms, they interact different. Like the response will be different, and it will vary from atom to atom. So for this case, instead of a single spectrum around this resonance frequency, let's say we have similar, so we have seen two level energy atomic system. So we have an resonance frequency around nu zero. So instead in homogeneous broadening, what we see a single spectrum around this resonance frequency. But in case of inhomogeneous broadening, what we'll see, in addition to this spectrum, the broadened spectrum around this resonance frequency, we will see a spectrum around other frequency. So if you see this graph, you see that there is a spectrum around this resonance frequency, as well as there are spectrum around other frequency that is close to nu zero. So you will get a spectrum like this, and this different kind of spectrum we got because of the different interaction of each atom with the radiation. So if you find out what is the net response, so for that what you have to do, you have to take the envelope. It is the variation of this peak. So we'll get a peak like this. And if you want to, let's take an example where we see the inhomogeneous broadening. So the first is the Doppler broadening. So the Doppler broadening happens. It happens because of the atoms, the atoms that is present in the system. They see different kind of frequency of the incoming radiation due to the Doppler effect. So in the atomic system, it's not like the atom is stationary. It moves. It vibrate around this atomic system. So it's not like it is at a rest. So depending on the velocity of different atom, it's like some atom may move upward, some downward, and some will move towards the left, and some will move towards the right. So depending on the velocity of the vibration of the atoms in this system, what we'll get that the because of the Doppler effect, like the Doppler effect is nu zero 1 minus nu z by c. So because of this Doppler effect, each atom will experience different frequency, which is other than this mu zero. So because of this different frequency, we'll see a broadening in the system. Okay, we'll discuss in detail what is Doppler broadening in the next few slides. So for now, we can take Doppler broadening as an example of inhomogeneous broadening. Okay, and the next type of inhomogeneous broadening we see in is lattice where there is inhomogeneities. Like inhomogeneities means the density of atom is different in different location. So inside the same atomic system, we have different density at different location. So if you see the figure here, and if you see the green shaded region, this region, so if you see the region one, the atoms here are more compactly packed. Okay, so that means the density here is more And if you see the orange shaded region here, if you see the region 2, the atoms are dispersed in this region. So because of this variation of density, what will happen? So instead of the discrete two-level energy, so if you are considering two-level energy, so instead of this two discrete energy level, we'll see a spreading of energy level because of the different density at different locations. So this is what shown in this figure. So we'll see there is a discretized energy level. There is multiple energy level around this frequency. So because of this multiple energy level, what will happen? This atom, they will also experience different kind of atomic resonance. Okay. So because of this different, instead of, so earlier we have only one atomic resonance, which is mu zero. So which correspond to, let's say, initially we had, let's say this level, this two level only. Let me take, so initially we have only these two level. So for that we have mu zero as a resonance frequency. Now, because of the different density of variation, we'll see this level will get splitted. So it's shown in this figure, this will get splitted and the lower level will get splitted. And now the transition will occur from this to this, from this to this. So because of this different transition, we'll see the different atom now, they will have different atomic resonance frequency. So that is why we see different spectrum in the line spectrum. Okay, so we'll see different resonance frequency in addition to the main resonance frequency, which is mu zero. So this is the case, and this we observe in a doped. Let's say we observe in a doped system, like when in a solid state level, if you say a neodymium in a yttrium aluminum garnet, there we'll see that there will be such kind of behavior of this spectrum. So we'll see inhomogeneous broadening there. And another system is erbium in silica, where we put erbium atoms in the silica matrix, and for that also we'll see an inhomogeneous broadening. Okay, and what are the different application of this inhomogeneous broadening? So we use this in the WDM application. So WDM is nothing but is wavelength division multiplexer. In a WDM, what we'll do, we'll pass incoming radiation of different frequency through a optical amplifier. And what we'll see in the output is that these nu1, nu2, nu3, and nu4, they are amplified in this manner. So if you see the graph, there is a, let me take different color. So we'll see a gain spectrum like this. So you see that the nu1, nu2, nu3, and nu4, they are amplified almost equally after going through this optical amplifier. Okay, so if you now in this system, let's say we are um, increasing the intensity of nu1. Okay, let's say we are loading the system. Like that is, we are increasing the intensity of nu1. So previously we saw that we've seen that if you increase the intensity, the gain will gradually decrease, right? The gain will gradually decrease like this. So if you see the gain spectrum, or let me show the graph clearly. So you know this gain spectrum, gamma nu versus nu. Now if you increase the system, the gain will gradually decrease. So for that, if we load the system, so initially we had gain spectrum like this. If you load the system, let's say we are loading at nu1, that is increasing the intensity at nu1, what we'll see, the gain at nu1 will decrease. But the gain at nu1 will decrease, but the gain at other frequency, it will remain unaffected. So that is the advantage of this system. That is the loading at one frequency is not affected by the gain at other frequency. Okay, so in this way we can get almost equal high gain in a WDM application if you take inhomogeneous medium. So this is one of the application of this inhomogeneous, that is the doping medium. If you take a doping medium, we'll get inhomogeneous broadening and will apply, we can get an application in WDM application. Okay. So till now, any doubts in the concept? Yeah, otherwise, let's move to the types of homogeneous broadening as well as inhomogeneous broadening. So homogeneous broadening, we see there is a broadening around the atomic resonance. So we can further divide this homogeneous broadening into three types. One is lifetime broadening, collision broadening, and thermal broadening. And for inhomogeneous broadening, we have two types. One is Doppler broadening and the broadening due to inhomogeneities. So let us look at each broadening one by one. So we'll try to cover lifetime broadening. Then we will see the rest in the next section. So for the lifetime broadening, so let's see what is lifetime broadening. So you have, let's consider the spontaneous emission case. So you have two energy level. So the energy level of your excited state is E2 and energy of the ground state is E1. Now, when it make a transition from higher to lower energy level, so previously we have considered only the radiative transition. So there are two types of transition that will happen. Like, so when the atom make a transition from lower to higher, the transition may be a radiative transition or it can be a non-radiative transition. Okay, it can be radiative and non-radiative. Radiative means the extra energy. The extra energy will be emitted in the form of photon. And non-radiative means there is no emission of photon in that case. So the energy will be lost in form of some other energy like phonon, lattice vibration, where there is no involvement of photon. So radiative means there is a emission of photon and non-radiative means there is no emission of photon. So it can be two types. One is radiative, other one is non-radiative. So for radiative case, if you recall, the dN2 by dt, that is the rate for spontaneous transition is given by minus of AN2, where A is 1 by TSP. And now if you consider that there is both radiative and non-radiative transition that is happening during the uh, transition of atom from higher to lower. So there is both occurring, like both radiative is occurring and non-radiative both are occurring. So in that case, we can write the rate equation is dN2 by dt equal to minus of AN2 and minus of SN2. So SN2 correspond to the non-radiative part. A is for the radiative part, S is for the non-radiative. So you can write this whole expression as T. So T is nothing but Tn2 equal to An2 plus Sn2. And similar to the A, we have defined A as 1 by Tsp. So we can also define the rate constant for the non-radiative case is 1 by tau nr, where tau nr is the lifetime of the non-radiative transition. So this means the total rate constant is T equal to A plus S. Now, if you put the expression for A, which is 1 by TSP, and S for 1 by tau TR, so we'll get the net time constant for this whole process, both radiative and non-radiative process. So if you put this, if you solve this dN2 by dt equal to minus Tn2, you get N2T equal to N0 e to power minus theta minus Tt. So previously what we had, when we had only radiative process, we had N2T equal to N20 e to power minus AT. So now we had, in case of both radiative and non-radiative, we have N2T equal to N20 e to power minus TT. Okay. So, and similarly, we can represent this rate N2T as in this form. So this is what is called this tau L, which is this one. T equal to 1 by tau L is the lifetime of a level. This is the lifetime of a level. So this lifetime 1 by tau L, this is both radiative and non-radiative part. 1 by tau NR as well as 1 by TSP. So this have two contribution, one contribution from radiative part and one contribution from the non-radiative part. Now we'll see how this lifetime of a level will have how because of this non-zero lifetime of a level will get a broadening. So we'll see in the case. So we have considered two level. So now we have N2T equal to N2T equal to N20 e to power minus T by tau. Okay. So you know, most of you have known the intensity. The intensity of a transition, it is directly proportional to what is the number of photon in the state. So that means IT is directly proportional to N2. So this means that you can also write IT in the same form as you write N2T. So N2T you write it as N20 e to the power minus T by tau. So in the similar manner, you can also write IT as I0 e to the power minus T by tau. And I is nothing but it is proportional to square of the electric field amplitude. So that means if you have an expression, so let me erase it. So you have an expression like this, IT equal to I0 e to the power minus T by tau. You can write the expression for the electric field ET as E0 e to the power minus T by 2 tau L multiplied by e to the power I 2 pi mu naught T. So this is what we got from this. So now if you take the square of it, this square will get. So the reason why we taken this expression of it is if you square it, we will get E0 square e to the power minus T by tau L. And this exponential factor, it will become 1 when you take the mod of this exponential term. So that means you can write it, you can write E0 square as I0 e to the power minus T by tau. So we get back the same equation that we had here. So that's why we have taken this expression. Okay. So now to find out what is the variation of this expression for this electric field in the frequency domain. So for that, what we have to do, we have to take the Fourier transform of this ET. So this is how you can take the Fourier transfer. So Fourier transfer is you want to go from time domain to frequency domain. So you can take the help of Fourier transform to get the expression. So if you want to find out what is the how the electric field is varying as a function of instead of time, if you want to find out what is the variation of electric field in terms of frequency, you can use this equation and you can find out what is the expression for E of mu. So if you now put this ET, this expression here, put this expression here. So if you solve it, what you will get an expression like this. And to take this integration is easy. There is only a one variable, which is t here on the right hand side. If you integrate it, you will get the E nu as E0 1 by 2 tau L plus I 2 pi mu minus mu 0. So this is the expression we'll get. And for the intensity variation as a frequency, we have to take the square of it. If you take the square of this intensity, we'll get the I nu as this. I nu equal to 1 by this expression. And now we want to see how this line step function is coming because of this lifetime broadening. So now we have to relate the intensity with the line step function. So this intensity and line step function, you already know these are directly related. If you go through the previous expression we had earlier, you will see that I nu and G nu are directly related. So that means you will get G of nu as this. This is some constant L with same I of nu. L is a proportionality constant. And the normalization condition, and you can get the value of L by taking the normalization condition. That is, if you integrate G of nu, that is G of nu is nothing but the probability. If you integrate it over the whole entire spectrum, we'll get 1. And if you integrate this, if you put this expression here and integrate it, you will get L as 1 by tau L. Okay. So the final expression that you will get is G of nu is put the value of tau L, which is 1 by tau L, and this whole term. So this is the final expression for the line step function. So now you got how the line step function depends on the lifetime of a level. So because of the finite lifetime of a level, we got there is a broadening that will get. So this is, and this expression is similar to what we see in Lorentzian distribution, which is shown here. So G of nu, we will see a peak around this frequency nu equal to nu zero, and there will be distribution of probability around the other frequency. And if you want to see what are the characteristics of this line spectrum, so G of nu, as you have seen, it is Lorentzian, and it is maximum at nu equal to nu zero. And if you want to find out the maximum value, you have to just put nu equal to nu zero. So this second term will be 0, and we'll get G of nu zero as 4 tau. And it is symmetric in nu. And if you want to find out what is the full width at half maximum, what you have to do? We have to do this is the variation of G of nu. So G of nu, show this equation. G of nu is given by 4 pi tau, 4 tau L divided by this factor. So full width at half maximum means the value at which G of nu becomes G of nu by 2. So G of nu becomes G of, so maximum value, uh, so maximum value we got, it is 4 tau L, and G of tau 0 by 2 means 2 tau L, right? So 2 tau L will get if you take this factor as 1. To take it as a 1, what we will get? We will get G of nu as 4 tau L divided by 1 plus 1, so it is 2 tau L. So that means for full width or maximum, we have a condition this. Okay, this is equal to 1. Okay, and from this, if you want to find out what is the delta nu. So delta nu we can find out by using this expression. So if you simplify it, you will get an expression like this. Newman, delta nu is nothing but nu minus nu zero. And if you simplify it, like if you put, if you take the square root of this whole expression, what you will get? You will get this. So 4 pi tau L delta nu by 2 equal to 1. From this, you can get what is the delta nu, which is the spreading of this line step function. It is depends on the tau L as 1 by 2 pi tau L. So here in this expression, you can easily see delta nu. It is related to 1 by tau. Okay. So because of the finite lifetime of a excited level, we are seeing a spreading of this energy level, spreading of the emission and absorption spectrum. So this is what we got uh, by considering the lifetime of a level. The broadening happens due to the lifetime of a level, and you also get it. You can get the broadening from using the uncertainty principle. If you use the uncertainty principle, you can easily get this expression. Okay. So this is all for today. Till now, do anyone have any doubts in this section? We'll stop now because it's already 6. So we'll discuss the other concept as well as some problems in the next section. So we'll have section on each Saturday, 4 to 6. So in the next section, we'll discuss what are the remaining on the slide. So do anyone have any doubts? Whatever taught in this section? If not, then we'll end the section now. So thank you for joining the section. Uh, we'll see the next concept in the next Friday, Saturday. So bye everyone. So now I'm ending the section. Okay.